My name is Francisco Capucho, and I'm working as a researcher at Instituto Superior Técnico. My academic background is in material science and engineering. I am a passionate volunteer, being working for Erasmus Student Network for the past 4 years. My newly founded love is 3D printing, and since I own my 3D printer, I've been printing awesome stuff all the time. Hi everyone! After a brief description of the main input-output methods applied in environmental management, we will now demonstrate succinctly the procedures to compute the block diagrams and present an introduction to the concept of cleaner production. The convention of the notation of block diagrams is the use of block letters for operations and the use of numbers for input and output. The calculation of the specific consumption are made in the following way. The specific consumption of a certain operation is the ratio between the energy consumption of the operation and the mass it produces, whereas the specific consumption of a certain material that is input to an operation is the ratio between the energy consumption in previous operations and the mass of that material. The calculation of mass functions are made in the following way. The residue formation factor is the ratio between the sum of materials that are input to an operation and the mass produced by that operation, whereas the mass proportion of a given material that is input to a given operation is the ratio between the mass of that material and the total material that are input to the operation. For instance, if we want to calculate the specific energy consumption of material 2, we must know how much is the energy flow of material 2 and the mass of material 2. And for this, we might have to know how much operation A energy flow is and the energy flow of material 1. Therefore, for the specific consumption of material 2, we need to know the specific consumption of operation A and material 1. Usually, industrial processes are not limited to sequential processes. We might have convergent and divergent processes. The analysis of convergent connections makes it necessary to know the mass proportions of the flows, which joins the operation since they can present different values of the specific consumption of the product. If we want to calculate the energy-specific consumption of material 5, we must now know how much is the energy flow of material 5, the mass of material 5, and for this we may have to know how much is the specific consumption of operation C, material input 2 and material input 4. The specific consumption of material 5 is then the sum of the direct energy used in operation C and the indirect energy used to make available material 2 and material 4. In a divergent process, all products that are an output of the same operation have the same specific energy consumption. What if we want to calculate the specific consumption of a residue output? While in reality there is a specific consumption for the residue output, in block diagrams it is convention to be considered null. All the additional energy that was used in non-useful outputs, for example residues, is stacked and count for the useful output, in this case material 2. All the energy used to create material 2 must be considered, including the energy that was wasted on the residue formed in that same operation. For example, by reducing residues, the amount of wasted energy decreases and the process efficiency increases. When calculating the specific energy consumption of a useful output, the value is multiplied by the residue factor, thus guaranteeing that the energy used to produce the unused residue is included in the useful output. Will the residue specific consumption remain null if there is a treatment operation? Well, the treatment operation has its own specific energy consumption, and it's the ratio between the energy used in the treatment operation and the amount of residue formed. But again, by convention, this specific consumption is included in the useful output. Therefore, specific energy consumption of the treatment operation is considered null. The recycling of products is not different from any other operation directly related to the production process. The methodology presented assumes that in a subsystem of recycling, the specific consumption of a raw material is still nil, meaning that the entire energy consumption of the treatment operation is attributed to the unitary operation that generates the useful output that results from it. The energy interest of recycling arises when the energy used in the process is lower than the energy used to manufacture an equivalent product. In this sense, recycling cycles should be as short as possible since the recycling product replaces products with higher specific consumption, but also reduces the mass in upstream operations. Cleanup production is a continuous application of an integrated preventive environmental strategy towards processes, products and service to increase overall efficiency and reduce risks to humans and the environment. It is a strategy that aims at reducing environmental impacts and impacts on health and safety resulting from products throughout their life cycle, from the extraction of raw materials to their elimination. For services, it involves incorporating environmental concerns into the design and the delivery of them. It includes concepts as minimization of waste production, eco-efficiency, pollution prevention, and green productivity. It implies a change of focus from the usual question, how can we handle our waste and emissions, to a more preventive questions of where do waste and emissions come from, how to avoid them, and in last case, what to do with them. The principles that should guide the application of measures to achieve cleaner production are to increase the energy efficiency, decrease water consumption, separation of waste produced, closure of material cycles, and the use of waste as raw materials. Addressing the source avoids the creation of the problem. Reduced energy consumption and good handling of materials will also reduce the cost affiliated with handling and disposal of waste. If this is impossible, the generated waste or the excess material should be recycled either internally or externally. This means that the source reduction will lead to a more environmentally friendly and more cost-effective production than recycling. Cleanup production can be implemented by following 5 implementation levels. 1. Planning and organization, which involves commitment of management and involvement of employees and setting up goals. 2. Opportunity evaluation, which involves procedures such as identification of the source of the pollution and identification of the causes. 3. Feasibility analysis, which includes technical and economical evaluation, and lastly, environmental assessment. 4. The preparation of an implementation plan and the implementation of the measures. And finally, level 5, which involves the evaluation of results and the new cycle of interaction, which involves monitoring and implementation support. So that concludes our brief look at level 1 of the CAPSTAN model. The next video in this series will move on to level 2 and how to shift to a more sustainable material and design of products. Thank you for your attention.